So for the Doppler effect, if I'm stationary, we have a sound source that's coming towards us. The sound source, what we saw before, is if I have a stationary source, the sound comes out at regular intervals. But now if my source is moving, what's going to happen is these intervals are going to get compressed. And I'm going to hear something that's different. Now, as I pass by, my sound actually gets bigger. That wave gets bigger. So if you have the PowerPoint or you have your book section, because some days I can do this better than others, as I am moving towards the person, it's going to look like the wavefront gets compressed. If I'm moving away from the person, it's going to look like it gets bigger. You can go backwards and forwards with this because we have 3 cases. You get 3 cases with the Doppler effect. One is I have a stationary observer and the sound is going by like that. You get that sound. Or I have the fact that I have a stationary source and I have a person on a bicycle coming through and it's moving. So this is the observer, this is the source, this is the observer, and this is the source. Or I can be like I'm in the car, and I'm in the car, and the ambulance is coming towards me. So we're both moving. We get both of us moving. So we get 3 different cases. Now for the case where the observer is moving, the frequency that the observer hears is going to equal the frequency of the source. And this is the velocity. So this is the velocity of sound plus the velocity of the observer divided by the velocity of sound. And this is equation 1410 in your text. Now, if I have the sources moving, I'm going to have the frequency that is observed is going to equal the frequency of the source. This is the speed of sound minus the speed of the source. So this is the source. And this is 1411. The general equation when you have both you can combine the two and you get something that looks like this. Speed of sound, speed of the observer, speed of sound minus the speed of the source. Now, when you work these problems, and this is 1412, and when you work these problems, the trick is the positives and negatives, because these velocities to be the problem. I will tell you that when I work these today, I have to double check and if galaxies are moving towards us. We can actually look at the shift in the frequencies that we get. We get a red shift or a blue shift if we're talking space, but we hear that change in frequency. Now, remember, frequency is related to pitch. So that's what's going to give you that sound as you hear something going by you. So that's the Doppler effect. Now, one of the labs we're going to do next week, it's going to be another activity. You're going to go out and get an example of the Doppler effect. And so this weekend, if you're out there and you happen to hear a siren coming by your house, you might want to hit record because you want to get an example of the Doppler effect. You can get, it's really kind of entertaining because I've heard the Doppler effect with geese. You can hear the geese fly by and you can hear the Doppler effect with geese. You can hear a Doppler effect with birds. Heavy equipment as you walk by as you're out there playing with your 1 over r squared, if you're walking past your sound source, you can hear the Doppler effect. So one of the things that we're going to be doing next week is capturing examples of the Doppler effect, because you can see it. I've had people do it with babies crying. They're walking down the hallway. I've had people use there's the really good one on the web that deals with bicycle bells. That's out there, but definitely for effect in your everyday lives, and if you're out over the weekend, especially getting close to 4th of July, we're going to hear all kinds of different sounds and July parades are going to be everybody's horns down parades. And one interference. And most of us, if we go to the pond and I have a ripple, we've seen these ripples before, and we see that we'll get what we call an interference pattern, where the waves will increase or decrease. And if you've ever been to a wave pool, you've seen that as well. Waves will increase or decrease. So if I have a wave in a string, and I'm sending a pulse down the string, and I've got a pulse coming from the other direction, as these two things come together, what you're going to see is you'll see these two things additive. And then at some point, the wave is doubled, and then the wave is going to move on just like it had done before. So waves will add. And this is called constructive interference. Now, we talked about that if I send a wave and it goes and it hits a pole, it's going to flip. And now I've got this situation. As the waves come together, you might see something that looks like this, and then you might see something that looks like that. And this is destructive interference. So I can have constructive interference and I can have destructive interference. And I am going to be able to deal with this waves being additive. And this is essentially what sound canceling headphones are doing, that we are optimizing the destructive interference so that we're canceling out the sound, that you're not going to be able to hear it. So we get those sounds that are out there. Now, I can set up what we call resonance frequencies. Okay. If I have a string here, we can create what we call standing waves. And if I do that, my standing wave, we've seen them before. And my string will vibrate, that I'll get a standing wave that looks like this. This is called a node, and this is called an antinode. But for waves in a string, this is going to be a string. My first harmonic is only half a wavelength, because remember, I have to have a complete wave, but this is only half a wave. What you're seeing here is this part of the wave that's being set up, and that would be a full wavelength. Now, my resonant frequencies are where I create this standing wave, and I can have a standing wave that looks like this. This would be my second harmonic. And then you can create a standing wave that looks like this. And that'd be a third harmonic. Now, what's interesting about this is that we're talking integers here. We are talking integers. And so we can do this as n times the wavelength divided by 2, and this will give us our harmonics for waves in a string. And it's something we're familiar with, and we can say these are quantized, because we're dealing with, I won't get a standing wave if I'm not dealing with this integer pattern. So we can generate these standing waves. Now, if I'm dealing with waves in a string, it's going to depend on the tension in the string, which we know, because if I play guitar or I play piano, depending on that tension in the string, it's going to give me what kind of standing wave I'm going to be able to set up. I can do the exact same thing in pipes. The pipes are a little different. If I have two open ends, I have to have antinodes at the open end of the pipe. So for pipes, antinodes are at open ends. And nodes are at closed ends. So if I have a closed pipe, so if that's a closed pipe, my first harmonic is going to be 1/4 of a wavelength. This one is still, if I have both open ends, I still have only got half a wave. But I can set up my structures to get the very same things that I get for my standing waves. And we played with those before. And those are air columns. That's why you're going to get a vibration that's out there. That's why we're going to get things that are a little different. In your text, we've already talked about timbre, and that's like color. And beats are another interesting thing. And these are when you have two frequencies that are just off of each other, or slightly out of tune if you want to think about it, and you'll hear this bump, 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 bump sound when you listen to it. It took me a long time. I don't have a very good musical ear, and I had to play with sound generators in order to be able to hear beats, and you're just off of getting these nice resonant frequencies for our sound waves. In your supplemental videos that you do have a really good explanation of the human ear. So for those of you that are dealing with medical things, you might want to go ahead and watch that. That's an excellent one. But that gets us through our waves and sounds, and we're going to start electrostatics on Monday. Question?